Well, welcome everybody to this NetPlay seminar. Today we have Francesco Coghi from the Nordic Institute of Theoretical Physics up in the north in Sweden. He is currently a postdoc research fellow there, and he's talking about rare but maybe not so much rare after all events in science and academia. And after this talk with such a catchy title, we will discuss postdocs and PhD fellowships, but that are independent fellowships. What are those kind of fellowships and the advantages and disadvantages, I suppose. So, well, Francesco, the floor is figuratively yours.
Okay, so you can hear me, right?
Yes.
So thank you for the introduction. Thank you for having me. And yes, so you're right. That was a catchy title. This is the one displayed right now is the title of the talk. But still, I'm going to talk about let's say a bit of what I do. Well, maybe it's better to say I'm going to talk about the background of what I do. Which is essentially I study rare events in large deviation theory. Okay, so here's a quick outline of what I'm gonna discuss. I'll give you some motivations. We'll go through we'll have a very quick overview on the large deviation theory, and then we will see some applications in network science, as indeed I only work tangentially in network science. I'm not a network scientist at all. I've had the chance to do some projects in network science, but that is not my main occupation. So I hope I won't. You'll still like the talk somehow. Okay. What are these rare events? One can say that all extreme events, by definition, should be rare. Okay, and this is where I'm gonna start from. However, I also want to point to the other arrow. I mean, it's not written anywhere that all rare events should be extreme. Okay, but let's focus on extreme events first. So on the here's a few pictures. On top left, we have a heat wave that hit China maybe a couple of years back. And then we have a hurricane on the top right. And then we have a pretty devastating flood that hit Louisiana, I think 2019 or something. And then another catchy picture on the bottom right, where you see, so there is this sailorman on the top bridge of a boat taking a picture from the window, and what this guy sees is this huge freak or rock wave. And I it is nice to see that on the right here we have this poster of an American movie. And essentially, it's the first time I see a poster that is not exaggerating the reality of what it has actually happened in nature. But these are all catastrophic events in a way. I don't know much about Greek mythology. Most likely you know more than me, but there's a little there's a little something that I want to tell you here, is that not necessarily all bad things come to hurt, right? To hurt us. So on the left you have this guy. This guy is Damocles, and this is the sword hanging on top of Damocles' head. So Damocles used to go to parties at Dionysus' court. I don't know when, but many years ago, and he'd just go around, eat stuff, and maybe suddenly this sword would drop on his head, and Damocles would die out of that. So Damocles, from this point of view, is an extremely fragile system. The sword drops, Damocles dies, full stop. In the middle we have Phoenix. Phoenix is a well-known legendary bird that is known to be able to reborn from her own ashes. So in this sense, Phoenix is a robust system. When it dies, it's easily reborn and it gets back to the same shape. On the right, we have Hydra, which is this serpent-like monster. If you chop off one of her heads, two heads grow back. That means that this system somehow is able to benefit from a sort of bad feedback from getting hurt. And when it gets back stronger. So these kind of systems have been dubbed as anti-fragile systems. And in this sense, not all bad things come to hurt us. So anti-fragility was a concept introduced by Nassim Taleb. I think the guy is now a professor at Cornell, and he introduced the concept to explain some financial market stuff. I'm not going to go through that. But that concept, besides financial markets and Greek mythology, finds a lot of ground even in natural sciences. So here we have an example coming from biology. On the left, you have an histogram that relates to the proteome, that is all proteins inside E. coli. And the histogram is telling you the number of proteins as a function, essentially as a function of the length, the size of this protein. So you see that maybe with a bit of imagination, you see that that distribution is at least bimodal. You see that you have a lot of proteins that are very short, and then you have quite some proteins, you have another peak for very long proteins. And one would, I mean, the question that would come is, why do we have such a long protein? So when you have a long protein, this is actually a flexible polymer in a way. And it's this flexibility that comes into play in explaining why it is so important of having very, very long proteins. And this is because when, and you see here on the right, I mean, this is just a sketch of the lifetime of a cell. You have, and inside this slide, you have organelles, and I mean, what is depicted there are proteins, like these dots. So the cell duplicates, and then duplicates again, and at some point, part of the, I mean, certain cells will just naturally die, and when this happens, proteins essentially get deformed inside the cell. So the fact that you have very long proteins actually help this, because without knowing the future that the cell will go through, maybe the cell will die or maybe not, having a lot of flexibility in this sense is helping the cell to face different kind of futures. On the one hand, the cell will survive, so the flexibility will give the possibility to the protein to serve very different functions. On the other hand, having a flexible protein is easier when you need to degrade it because the cell is dying. So flexibility is as tinkering in a way in biology. So systems that in a way benefit from feedback. Okay, but now let's go into the much. I'm not gonna be super formal, so I think I've tried to make it out that most of us can understand. So suppose that you flip a coin, an unbiased coin, n times, and you are interested in the number of heads coming up out of this experiment. And well, you can fully calculate the distribution of the number of heads over these n trials. And this is just this binomial distribution. And we know how also to calculate the standard deviation. So we know that having n, an experiment of n, of having, let's say, flipped the coin n times, half of the times, on average, we will have heads. But then we want to understand how this number, I mean, if we run an experiment, we will have not exactly that number in average, but we'll have fluctuations. And one can understand fluctuations through standard deviation. So standard deviation is a measure, essentially, that is telling us how likely it is to have a fluctuation that is of the order of the square root of the size of the experiment. But these fluctuations, in a way, are typical fluctuations. They happen more often than the kind of fluctuations that large deviation theory can explain and tell us. Indeed, when we are interested in the number of, when we're interested in fluctuations that scale with the system size, think, for instance, the probability of the probability of having all heads or tails, then in that case, what you're looking at is a rare event in terms of large deviation theory. And this is not covered by the standard deviation or the central limit theorem, if you like. It goes beyond that, and this is the kind of rare events we want to look at. But as I said, it's not that all rare events are of interest. I mean, not all rare events can be explained through large deviation theory. So what are the kind of rare events that are easily explained by large deviation theory? And in order to understand that, I've put here in bold, persistence is key, not only in our life, in science, but even in this theory. So on the left, you have a it's China, and you have, so it's a map of China, and you have different regions, and these are colored depending on the highest recorded temperature in July, I don't know, in some years. So this is a record. This is an extreme. That is fine. It's certainly a rare thing. But large deviation theory is not really dealing with this kind of rare events. Large deviation theory is dealing with this kind of rare events. So here you have Greece, and again, the map is colored. This is the color scheme, and you have that the darker the color, the longest. So here we are talking about heat waves. The longest the heat wave that hit that particular region. So this is, I mean, in a way, this is also extreme. If you have many days in a row that lead to a very long heat wave, then that is certainly an extreme. But it's very different from this kind of extreme here, where you have one single, essentially, record. Here you have many days that are deviating from the average. So it is this that is important in large deviation theory. It is having many small deviations from the typical behavior, in a way, that lead to a rare event that we can explain with large deviation theory. Persistence is key. That is why I decided to put that word. Okay, so let's have a quick overview about large deviations. So large deviation theory is a very well-known theory so far. I mean, it's been developed in the last century. It's still growing, but the way it's been developed is interesting. We've had somehow two different communities. We've got physicists on the left here, and mathematicians on the right. These people have not really discussed with each other for a very long time. You for sure will recognize name from physicists and of certain mathematicians, but it's only recently, I'd say maybe starting from Ellis, that a sort of cross-fertilization between physics and maths have come. And so nowadays it's a very nice field to work in, because you see mathematicians and physicists essentially collaborating, and I very much like it because of this reason. Okay, there are plenty of books if you want to study the theory. There are more mathematics books like this one, or maybe this other one. But there is also physicists like more oriented to physicists book here on the bottom right. But if you if you are a physicist and you want to face large deviation theory for the first time with a keen eye to mathematical detail, I should maybe refer you to this review, written by Hugo Touchet back in 2009, I think. Yes, 2009. Okay, now let's get to the core of it. So what are we talking about when it comes to mathematics? I promise we are not going to see many more formulas than this. So large deviation theory deals with the exponential decay. So our events should exponentially decay in the large. So it's about this exponential decay of large fluctuations in sums of random variables. So suppose you have a sequence of random variables and put them all together, call that stochastic process. And now you define an observable that is essentially a sample mean of a particular property f of those random variables. Okay, so this is like a sample mean observable, if you wish. And what we are interested in here is the distribution of this observable. And what we know is that in the long, so for a very long sequence, essentially for a very long stochastic process, for a very big system, the scaling observable can change depending on what we look at. The leading behavior in the distribution is essentially exponential. So you have n, that is essentially the size of the system. The bigger the n, the closer essentially you go to the typical value. You know, the law of large numbers. So the longer the sequence, the closer you go to the average, essentially. But then you have that fluctuations, because this holds at finite n. Fluctuations are distributed. You can actually understand the likelihood of fluctuations by looking at this function here now, that no longer depends on the size of the sequence you're looking at. So this function is the core object of large deviation theory, and it's called rate function, large deviation rate function. So what are the goals of large deviation theory? First, prove that such a formula can be written. So prove that the leading behavior of a distribution is exponential. Second, to calculate this rate function I. And third, to understand the mechanisms that lead to a particular rare event. So the mechanisms that lead to a value of A that is very far from the typical value. It is very hard usually to calculate this object here, the rate function. And the most used tool in large deviation theory is this theorem. It goes by the name of Gardner-Ellis theorem. And it says that instead of looking at the probability distribution, you can look at the scaled cumulant generating function of that object. This corresponds, I don't know, in statistical physics, it's exactly the same as moving from calculating the microcanonical entropy to calculating the canonical free energy. So the canonical free energy corresponds to this function here. And then you know that if you can calculate that function and if it's differentiable, then a large deviation principle holds. And much more than that, actually, thanks to a Legendre transform, you can just go back to your rate function. This is also what we do in statistical mechanics when we want to calculate a microcanonical entropy, a configurational entropy. We cannot do that. Then we introduce a certain temperature, inverse temperature. We do things in the canonical ensemble. We calculate the free energy, and we go back to the entropy with a Legendre transform. The mathematical formalism. What I'm saying is that the mathematical formalism behind statistical mechanics is large deviation theory in essence. And so here's an example quickly. It's just to show you the shape of these rate functions. How do they look like? Suppose that you have a sequence of independent and identically distributed random variables xi, distributed according to p of x, and then you look at this observable, which is another sample mean, and then you look at suppose that this p of x is Gaussian. If this is Gaussian, then the rate function is purely quadratic, which is what you expect because the central limit theorem holds. And so when you have a quadratic rate function, you have essentially a Gaussian distribution. So you're saying that this object is distributed as a Gaussian, full stop. But if p of x is not like Gaussian, then like in this case it's exponential, then the rate function is not just a quadratic function, it's still quadratic around the minimum of the rate function, but then you see that the tails are asymmetric. That means that certain rare events will happen more easily than others. Indeed, let's try to understand a bit better these functions. So the minimum and zero of the rate function is this mu, okay? It represents the typical value. Essentially, it represents the convergence point if you have a very long sequence. It's the average. Then the more you go far off this value, the more rare, essentially, the event you look at. So the higher the tail, the less likely is that event to appear. So and the lower the tail, the more likely is that event to appear. Okay, so this is pretty much the quick overview I wanted to give you on large deviations, and now let me go through a couple of examples in network science. So there is this beautiful theory. So, you know, in networks, people, I think, you look at structure and dynamics. So I decided to split these two things and look at this first. So let's look at the structure. So there is this beautiful theory. It was introduced in 2011. It's a large deviation theory for the structure of random graphs, of Erdős-Sérényi random graphs, in the limit of having a dense graph. We still do not know much about sparse graphs anyway. So let's take a question. Suppose that you pick a graph from the Erdős-Sérényi ensemble of n nodes, and then a probability p of just connecting these two nodes. And then you say, okay, suppose that now I fix the number of triangles on my Erdős-Sérényi graph to be a certain number, okay? And this number is TNP. On average, that object is just written this way. But then you don't want to look at the average. You ask, okay, what is the most likely structure that will lead, essentially that will host this number of triangles. So you take the number of triangles very far from the average, and then you ask, what is the most likely structure that will host those triangles? So there are two different scenarios here. I mean, that structure can be still Erdős-Sérényi in a way. So you have triangles spread over the graph, or you have a completely different structure that is no longer Erdős-Sérényi, and now where all triangles are somewhat clustered in a certain region. Well, and this is very surprising to me, depending on delta. So there is a double phase transition where if delta is smaller than delta 1, let's say, than a certain value, then you are still looking at an Erdős-Sérényi graph with triangles well dispersed. And this is also the case if delta is larger than another value that we call delta 2, it's still Erdős-Sérényi and very uniform in the dispersion of the triangles. But in between, it's no longer Erdős-Sérényi, and you have triangles essentially clustered in a single region. So this is just an example, and maybe I'll take another minute to do another little example about about the dynamics instead. So take a random walk and put it on a random graph. Okay, so again, take your random graph from a certain ensemble. Let's take this ensemble here. So we fix the number of nodes and put a certain probability of having an edge between nodes. And then you put a random walk on it. And you look, now the random walk will, in time, will just visit different nodes. And what you record is an observable that is the mean degree visited by the random walk over time. So at a certain time, the random walk will visit a degree 5. Next time is going to visit 7. So you take the sum, you divide by 2, and you keep on doing this. So it's the mean degree visited over time. And you want to study rare events of this observable. And here there is on the left. So what I'm showing you here is an Erdős-Rényi graph of a certain number of nodes. And then what I did was to color and size nodes depending on how much time, essentially how long the random walk spends on them. So this is the typical case. So if you run a simulation, a long simulation, you see that the random walk is somewhat very well spread over the graph. Of course, it will spend a bit more time in the most connected region of the graph, but it's very well spread. At finite time, though, what you assist is rare events, fluctuations, and it may well be that the random walk is actually fully clustered in a very low connected region of the graph. So what is interesting here is that when you, so there is a sort of dynamical phase transition. Consider, for instance, that you determine your dynamics, so how the random walk moves over the graph according to a certain temperature. There will be at a particular temperature that essentially will lead to a situation where these two phases, this phase and this phase, coexist over time. So the random walk at the same time, so so if you take a long trajectory, the random walk for part of it will be very well spread, and then intermittently it will be concentrated in a very low connected region, and then it will go back to being very well spread, back and forth. So we call this dynamical phase transition. A full proof of it is actually not derived yet, but this is what we believe is happening. I have another example, but I think I'm going over time, so I stop here. So large deviations, what we have seen, we can get the most probable values by looking at the typical state, that is the minimum and zero of that rate function. But we can also explain fluctuations and rare events in the tails of our rate function. I haven't showed you any rate functions in these two examples, in the last two network science examples, because it was a bit pointless. I hope I could at least convey some of the messages. And it is nice to see when, for instance, atypical structures emerge from ensembles. That is the first example I explained, I went through. And then you take a realization of a graph, and then you look at the atypical dynamics of a random walk, and this was the second one. So this is all from me, and I'm happy to take any questions should you have any. Thank you.
Wow, thank you, Francesco. Basti says thanks a lot.
Yeah, you're welcome, no problem.
I have a question about the last example. So there, what was exactly your order parameter?
Yes. So the order parameter in that case is a Laplace. It's this. It's k. It's a Laplace parameter. It's the parameter you use in your transform to go from the rate function to the moment generating function, to the cumulant generating function. Now, this is a bit technical, but you can think of that as essentially it's really very much like a temperature, where is a bit more complicated than that. So in a way, it is a parameter that it is allowing you to visit different states in your system. Temperature is not exactly is not correct, because I said temperature because I thought it'd be easier to understand, but it is not correct, because if you increase the temperature, I mean, you can intuitively, you can just say, okay, then I'll make my dynamics faster because the random walk is moving faster, and that is not what I wanted to convey. Thing is, that parameter is corresponds. I mean, if you draw a parallel in your mind with statistical mechanics, it corresponds to a sort of inverse temperature or temperature. But here it's really a Laplace parameter that you tune in order to visit different regions of the graph. Now, what you'd expect, though, is that, so in this case, we are visiting the random walk is well dispersed. And then when you move that parameter, you'll get to a region where the random walk is localized here. The problem is that there is a point where that parameter faces essentially a discontinuity, where both these two mechanisms happen at the same time. So if you want, you can write down the dynamics of that object. And when you write down, instead of having, suppose that pi ij is the transition matrix of your unbiased random walk, that parameter enters this way. So you write pi ij, then you multiply that by an exponential e k, the mean degree you want to, the mean degree of observable. It is that k. So by changing that k, you visit either all the graph or localized regions. Yep. So okay. I hope it's a bit more clear.
Yeah. I mean, I know the analogy with temperature was not exact, but it was useful. Okay. And I don't know if for other people that is attending the seminar this has happened, but for me, it's been completely new. This large deviation theory applied to networks. And my next question is whether, because the two examples that you have presented here are like very technical in the sense that are applied statistical physics to this problem. So do you know, or could you give us an example of these methods applied to real networks, or problems in real network, like traffic networks, neural networks, or something like that?
Yeah, that's a good question. I don't know. So what I know is that large division theory is somewhat still new in the field of network science. I mean, these are only a couple of examples. There's people have been looking into many different things. There is one example, though, that that now comes to my mind, and it's a paper. Yeah, maybe I can tell you about that. It's a paper from 2017, I think. Maybe I can show it to you.
Yeah,
Let
sure.
me see if I find it. It's just a picture. Yes, there you go. Okay, let me. Right. Okay, so let me share again the screen. So this is the paper. I don't know if you've ever 2016, sorry, not 2017. I don't know if you've ever heard of it. So in this paper, you just look into I think it's a SIR model. No, it's SIS. So you have sort of epidemics. You have spreading of an infection over a network. And what the guys here want to study is how can we control and how can we make it happen? How can we make the extinction happen over time? So suppose that at a certain time you have a certain amount of nodes that are infected. You want all those nodes to recover, well, to go back to the susceptible state, essentially.
Okay, you look for the extreme event in which all the susceptible nodes, all nodes are susceptible. Okay.
Exactly. And what the so it is still not done on real networks, but maybe it's an easier application to understand. And what they do is they show, okay, let's look at this picture. So on the right axis, you have the number of nodes of a high degree. I don't remember how they define high degree. Anyway, the number of nodes of high degree that are infected. And on the y-axis, we have the number of nodes of low degree that are infected. Okay, and you start your system at this around this this point here. So you're saying that at a certain moment in time, you have this fraction of nodes of high degree nodes, 0.7, that are infected, and this fraction 0.2 of nodes that are of low degree nodes that are infected. And they want to study the optimal way in time. So this is very much a large deviation problem. That you go from this state to the fully extinct, to the extinction state, that is 0 nodes infected. And what they show is that the optimal way to go there is first, maybe this picture is not the best one, but you see that this is sort of sigmoidal function. So first, what you do is you need to decrease the infectivity of low degree nodes, because you go up first. You see that it's a bit bumped up. Then what happens is that you rapidly go down in the number of high degree nodes that are infected. So you first approach low degree nodes and you remove the infection from them. Then it's time to look at the high degree nodes, and you move their infection from the high degree nodes. Here there is a sort of cooperativity between low and high. But then at the end, it is still the low degree nodes that are infected, so you should go back to the low degree nodes and decrease their infection. It is interesting to me that the first thing they do, the optimal way, is not to remove the infection from a hub. The first thing they do is to remove the infection from a low degree node, then hub, then again low degree nodes.
Yeah, it's anti-intuitive. Interesting.
Yeah. So this is the optimal way, the most probable way you can get rid of an infection. Well, okay, of course, this is all theory, right? Again, these are not real networks. But yeah, maybe so this example is a bit closer. About real networks, I mean, I've been struggling about that as well, because I've been working on this also with some other people, like Gabriele, Leonardo, this maybe you know these people. And yeah, I mean, I come from a very much theoretical side, so and they have very much applied questions. So yeah, I agree with you. It's
yeah, but it was fine. Okay, thank you. Very interesting application. We have some questions in the chat, Basti. I have a follow-up question to Violetta's first question. Oh, epidemics seems like a interesting application for large deviation theory, right? Okay, so yeah, it got solved. Okay. You predicted the application. Cool. Okay. Nice. So if there is no any other question or curiosity, we can go to the discussion part of the seminar if you agree.
Oh yeah, I do agree.
Nice.
I thought though I would keep this more as more interactive, as a discussion indeed. So I'd like to know among you people, how many of you are PhD or postdocs? So Violeta, you are a postdoc. Basti, you are a
First
PhD
year
student.
postdoc, so almost.
You both are
PhD.
postdocs, right? Okay.
Oh, sorry, Basti. I thought you were so sorry. Okay.
Then we have a postdoc
Another
second year.
postdoc second year here. Lisa,
Uh,
I know is PhD student for sure because she was in my research institute. So yep.
okay. Another PhD.
PhD.
Yeah, PhD indeed.
Yep.
Hi.
Hi.
So maybe okay. So and it seems like that you're towards the end of it, right? PhD third year. Okay, so I just thought, I don't know, what kind of position do you have, Violeta? Is that independent or
No, it's related to a research project.
grant?
Yep.
Okay. So I just wanted to tell you maybe a bit about this. I don't know, but again, let's keep it interactive. So when I was by the end of my PhD, I thought, okay, what I'm really passionate with research, so I really wanted to do some research, and then I thought, okay, what should I do? So I'm also somewhat independent on I am on what I do, and it's and at times I've also struggled a bit during the PhD because of a very sort of different kind of supervision that I wanted. So at some point I realized, okay, I think I'm gonna try with fellowships. So fellowship is a way to do I think to do your own research in an independent way. Of course, you need to win a fellowship to do that, but in the UK there is plenty. Depending on the country, you may have more or less. I don't know, for instance, I don't know of any fellowships in Italy. I know maybe of a couple in France. But yeah, the idea is that, so I applied for fellowships, I got a fellowship. And what happened is that, and I so far I have very much enjoyed it. So it's very much like doing this kind of research. Thing is, it is not something I think everyone is fit to, and so it's not a warning what I'm trying to convey, but being on an independent fellow, I mean, it was very hard to me too, because often it means that you do not have anyone to talk to, and of course nobody cares much about you because you've got your own money, your own projects, and maybe going through a fellowship at the beginning of the just at the end of the PhD is not for everyone. I've heard of stories of people just quitting because they couldn't go on, having no let's say having no feedback. If you don't have already, let's say, a good network of collaborators, it's a bit hard, and maybe at the end of your PhD you don't have this kind of network of well-structured network of collaborators, and so there are pros and cons. Pros come with, for instance, you manage your own time, you do whatever you want. I mean, if you have questions that you want answered and maybe people don't really care about those questions, well, you just maybe try and devote some time to that. And this is just very good. At least this is the part I like the most. But at the same time, and this comes as a con, as a drawback, is that at times you are very much isolated, and it is not always easy to get feedback from people, again, because you are not their own responsibility. yeah, so this is actually the gist, the message I want to give about these fellowships. I don't know if you people here have any thoughts on that, if you have ever thought of applying for a fellowship.
Oh, Basti has a question.
Yeah.
How did you choose or search for people group to work with after getting your fellowships? And
Yeah.
do you have to compromise with your research questions or topic
That's
to
a very good
accommodate
question.
with them?
Yeah, I don't think I have a ultimate answer to that question, but I can tell you what I did. So I'm now in my third year of the fellowship. So during the first year, I was very much focused on quite a few projects that I still had open from my PhD. During the PhD, I already got I was able anyway to build a good network of collaborations during the PhD. I traveled quite a lot. I met a lot of people, and so I kept on working on those projects. Then what I realized is that I mean, although those were lovely projects, there is one bad thing about academia. Well, bad and good, in my opinion, is that if you don't publish on high impact factor journals, nobody gives a about you. And yeah, I'll answer to that later. So I had to find a compromise there. I went to workshops, I went to conferences, I met other people. The way I do is just I talk to people. So I go there and I discuss with them. I ask them questions, they ask me questions, and here you start with maybe a new project. But then at some point I had to compromise because I had to move from a very maybe theoretical perspective to something a bit more of interest to people, or maybe a bit more easy to publish in a high impact factor journal. And then it wasn't easy because it was a compromise. So I started a few projects in that direction. And of course, those are not my favorite projects, right? I mean, it's a compromise. On the other hand, having such a compromise is good because at least you get to interact and exchange intellectually with other people. Otherwise, you're often isolated. The thing is, as a fellow, nobody knows about you, or very few people know about you. You may have good ideas, but still you're alone. And since nobody knows about you, in the beginning at least, nobody comes to you and asks you questions about your own projects, or nobody is really somewhat interested in doing something about your own projects. But it's the opposite. You go to maybe more senior people and you ask them what they do, and maybe they can benefit some large deviation theory in what they do. It's a compromise in order to get on good journals in a way, which I don't like at all as a compromise. But for me, it's also a compromise to have some sort of intellectual exchange with people. And then usually when you are a fellow, it is often the case that you find yourself in a very dynamic environment. So here at Nordita, we have workshops and conferences every day for the whole summer. So starting from end of March until end of October. And you keep on having people coming. So it's very easy. If you want to interact, it's easy. It's easy. The problem is that what are you interacting about? That's the question, I think. I'm sorry. And then there was another question, maybe in the chat.
Yeah, if you want, you can read it out loud
Yeah.
for the recording.
Oh yeah, I don't have any benefits. So usually, you're right. Usually, I don't think this is a general answer though. Usually fellowships are on a tax-free stipend, so you do not have this kind of benefits like parental leave or illness. You don't have this kind of benefits.
Oh, don't they?
No, I mean,
Oh.
at least I don't. But I mean, yes, so I agree. But in the end, it's your self-managing time. So nobody tells you off if you don't go to the office, because, I mean, it's your own time and you do whatever you want with your own time. On the other hand, I agree with you that often maybe, I mean, if you want to build up a family, then parental leave is a good thing. But I also know of fellowships though. That is why my answer was not general. So in my case, I don't have any benefits, but I know of fellowships where actually people are on a salary, and so they are actually fully employed. But even here at my institute, starting the year after I came, they started fellowships on a salary. So pros and cons also here. I mean, when you're on a salary, you earn a bit less, but you have benefits, social benefits, which in Sweden are amazing. I don't know, for instance, about the US, what kind of benefits maybe you still have parental leave, but I don't know how long they would give you. Maybe you know, Sneha, maybe you know how long they would give you for a parental leave. So here in Sweden, they give you up to summing both parents, you can get up to 500 working days or something, which is like 2 years. Of course, usually maybe the mother takes more in the beginning and then the father later. But still, it's a very good deal. I don't know anywhere else though.
Yeah, Sweden sounds great. Thanks so much. I am also not sure how the parental leave works in US, but what I know is like in terms of healthcare benefits, for example,
Yeah.
there are certain, I feel, discriminations between independent fellows and university employed postdocs or research associates. But yeah,
So,
Sweden sounds great though. Thanks.
yeah, no, in Sweden there is no difference. Maybe it's because I'm European, but I have all benefits of a normal employee. When I go to the doctor, for instance, I don't pay. Or I mean, I think there is a cap. I pay up to 1,000 crowns a year, which is 100 euros a year, which is nothing. And then that's it. And this is true also for an employee. So from the point of view of healthcare, yeah, maybe it's because healthcare in the US is not so, I mean, they try to make an effort at some point to make it public, but it's still very much private. So yeah, I understand that could be a problem in the US. Welcome. And Annalisa, you maybe you have a question, right?
Yeah, I have a very practical question. Where one can find those kind of fellowship? Which are those kind of fellowship?
Yeah. So the way I started, because I didn't know anything about fellowships, right? During my third year of as a PhD student, didn't know about fellowships. I didn't know what a postdoc would be. And what did I do? Hang on. I think back then, oh yeah, okay. So there is a newsletter. I think it is, right? Well, okay, partly through my supervisor, and then through newsletters. So there is a newsletter, statistical. Okay, this is not very much network science related, though. There is a newsletter of statistical physics that comes every Friday, and in that newsletter, but actually they post also a lot of positions in network science. So maybe you should look into that. And in that newsletter, they talk about fellowships. postdoc, on grant projects, plenty of other things like more senior positions, conferences, workshops happening, and this comes every Friday. I think that is a very good starting point. And then I think a bit through my supervisor in London, we discussed about that a few times, and I think she told me about this possibility of doing a fellowship. And she told me, okay, you should look into EPSRC, which is a thing that is very much known in the UK. UKRI is another thing. And then, I mean, if you want, I can give you a full list of fellowships. At this point, I know very many of them, and you can just look into them. Annalisa, where are you based?
It is in Palma de Mallorca.
Palma. Okay. But have you ever been to?
Yeah,
to
I
London?
mean, not yet.
I thought you
Maybe
visited at
in the
some
future.
point. Maybe.
No.
No. Yeah, I'm wrong. Okay.
Will be actually benefit also for our listener to have a list of this kind of fellowship. I think it could be a good resource if you can provide it.
Oh yeah, sure. I mean, it should be public knowledge, right? So I can
Okay.
I can give you a list I have, because now, I mean, my third year is coming, well, not coming up to an end, but soon next year I'll be jobless if I don't apply for other jobs. So I'm back to business in a way.
Yeah.
So I am looking, applying. Yeah.
Well, but 3-4
Makes
years
sense.
of a postdoc fellowships
Yeah.
is quite a lot, isn't it?
Yeah, it's usually 2-3 years.
Okay.
But yeah, so it was 2 years mine, but then it got extended of one further year.
Okay.
I mean, I asked for an extension, essentially because I didn't want to move last year. So I said, no, I mean, if I could have a further year, it would be better. They said there was no problem, but yeah, usually it's 2 years. I mean, I'm sure you know the Marie Curie fellowship, the European, the Global Fellowship. I think maybe the Marie Curie, I mean, it's very prestigious, but in my opinion, is the worst fellowship ever. Because it is mandatory to I mean, it's a mobility fellowship, so you have to move. And I mean, it's up to 2 years, right? I mean, once you move, 6 months are gone, essentially. I mean, my experience, and then the older you grow, the harder it is. So 6 months are gone. After these 6 months, you start doing some research, and after 6 months, you are back to business into applying for other positions. It's a joke, but it's prestigious, so people apply, and once they get it, it is easier. I was told to get to a more senior position, maybe a slightly more permanent position. But yeah, so I know quite a few fellowships, mostly in where I am right now. It is Sweden, UK, and US. So these are the places where I also know of. Maybe you know as well. I mean, there's another fellowship in Germany. It goes by the name of what is? Oh shit, I forgot. I forgot the name. Anyway, I'll write a list. Yeah. I don't know of any fellowships in Spain, actually.
Me neither. I know one in Portugal.
What is the name of that one?
It's in Lisbon, in the Guggenheim Institute.
Okay.
Because a friend of mine is doing that. And then I only knew the Omninar of the Santa Fe Institute fellowships, the postdoctoral fellowship, and that's all. I didn't know they were a thing in the UK, actually.
I think they are a thing if you look into that. I don't think they are very much advertised. I don't know. But as far as I know, I don't know if it's just because I spend a lot of time in the UK and therefore I'm a bit biased, but In the UK, I can find, yeah, there are the max. Yeah, that's true. In Germany, you can go to, I know Dresden, the Dresden one, but the one I meant was different one. It will come. Anyway, when I was in the UK, I could find many fellowships. Starting from the 1851, the Newton Fellowship, the Leverhulme Trust, at Cambridge they have 2 fellowships, at Oxford they have another fellowship. Of course, then it's richer universities that have more fellowships, because it's a bit I mean, you're not on a grant, so there is some sort of dissipation there, right? Yeah. Yeah, but anyway, I can write a list. It's no problem.
Is this your first postdoc
Yeah.
position?
Yeah, it is.
Oh, it is. Okay.
It is. Yeah, I graduated 2021, October. No, well, September. Yeah, September 2021. And then I moved to Sweden.
And for you, what was your main reason to take this independent fellowship? Because, for example, for me, I also considered briefly to apply to one, but basically what I thought was like, but I mean, Violeta, you do not have one idea, one research idea that you want to pursue. Now you are still learning, let's say like that, and you have a lot of projects that are not finished yet. So at the end, I choose one postdoc with ecology group because I wanted to immerse myself in ecology. So I thought that better to have an IP, a PI,
Yeah.
than being by myself. So in your case, what was?
So I've always worked independently, even during my PhD. So for me, it was more like a continuation of that. But at least, of course, during the PhD, I could talk to a bit more often with my supervisor, right? But and then I very much like working on things on things that I like. And there is this problem that if you apply for a project grant, you don't know if you will if you find yourself fit for that position, if you like it or not. And then another thing I thought is that, well, if I'm on a fellowship, in principle, I can collaborate with any people I want, and I can still learn from them, which is true at a certain extent. It's much harder because, again, you're not their own responsibility. So magari, so it may happen that they devote you a bit less time. They devote to you a bit less time, but it's still possible. Another thing that I think drove a bit my decision was that during the first year of my PhD, I had a very bad experience, a very bad supervision experience, and I was very much sure that I didn't want to repeat that any longer in my life. So yeah, so these were the things that helped me understand what I wanted to do back then. Welcome.
Okay. Well, actually, we are a little bit out of time. So, if there is there is no any other question, maybe we can call it a day, an afternoon.
Sure.
It's been a very interesting
Thank you.
topic,
Thank you,
the one that you have chosen. Yep. And
Yeah.
please, yes, if you send us these
Yeah,
links.
I'll send maybe to Silvia or to Gabriele the list.
Yeah, sure. And we will be very happy to put it in our website. Now we are planning to do a resource tab with all these little pieces of knowledge that we got.
And you should, I mean, I will send you my own list, but then you should, yeah, I mean, of course, the list I have is a bit biased towards what I do, which is more like maybe applied maths and theoretical physics in between them. but maybe it's a good starting point anyway for
Yeah,
people.
for sure. Yeah. Okay.
Okay.
So thank you very much.
Thanks a lot.
Thank you.
Thank you. Take care.
Bye bye. Bye bye. Thank you very much.
Bye.